In this video, we'll first look at modeling the total COVID-19 cases in the United States using linear and exponential models. Then, we will look at the growth factor and growth rate for the exponential model and make future projections with those numbers. Disclaimer: I am not a doctor and cannot give any medical advice. This video is only for educational purposes for those interested in stats. The data is taken from the CDC website starting with January 22nd through March 30th and is incomplete. This graph is a total number of confirmed COVID-19 cases in the United States. We expect this to be an increasing graph because we are accumulating the total number of cases found regardless of recovery or death. As we can see, the total number of cases began to noticeably increase starting around March 13th, when there was declared a national state of emergency. The graph clearly looks like an exponential function, but we will look at how it compares to a linear model first. In this graph, I use a linear regression model for total confirmed cases in the US. As you can see, the graph is a terrible representation of the total number of cases. The correlation coefficient is 0.59, which is a moderate positive correlation. This means that as the date increases, the total number of cases moderately increases. The R-squared value of 0.3482 means that 34.82% of the variability in the total number of cases is explained from the model. This value is generally considered a weak or low effect size, so most of the variability is not explained by the model. The next graph has the exponential model for total confirmed cases in the US. The model is being overlapped by the actual graph of confirmed cases, so that's why you can't see it. We can visually confirm that the exponential model is a great fit for the data. We see that the correlation coefficient is 0.932, meaning there's a very strong positive correlation between time and the total confirmed cases. This isn't shocking since every day new cases are being recorded. R squared is 0.8687, which means that 86.87% of the total variability can be explained by the model. This means that most of the variability can be explained by the model. Next, we want to discuss the growth factor and growth rate for the exponential model. But first, let's define these terms. The growth factor is the factor by which a quantity multiplies itself over time. For example, if the number of cases goes from 10 to 50, the growth factor is 5, since the number of cases were multiplied by 5. The growth rate is a rate at which the quantity increases or decreases over time. If we go back to our example, the number of cases jumped from 10 to 50. That means the number of cases increased by 40, which is 400% of 10. And that's the initial case. The growth rate is a decimal, so the 400% could be converted to 4. Next, we'll be calculating the growth factor and growth rate. The formula that is used to calculate the growth factor and growth rate is A equals P times a quantity 1 plus R raised to the T. And here we're going to consider where R is positive, since we're looking at growth. A is the amount after time T. P is the starting amount. R is the growth rate. 1 plus R is the growth factor, and T is time. Looking at the equation, for the exponential model, we have y equals 0 times e to the 0.1639t. We can find the growth rate and growth factor. So how do we do that? Well, we need to set it equal to p times 1 plus r to the t. Here, we don't care about the initial amounts, so we're only going to consider the exponential part. So they're both raised to the t power. Since they're both raised to the t power, we only look at the base. So for for e to the 0.1639 to the t, that can be rewritten as e to the 0.1639 raised to the t. Because exponent to an exponent, you multiply. Now the t's are canceled, and we have the equation e to the 0.1639 equal to 1 plus r. This means the growth factor is e to the 0.1639 or 1.178. So the growth rate is 17.8% or 0.178. Okay, how many days until the number of cases multiply? With a growth factor of 1.178, we will need to set the equation 1.178 raised to the t power to equal 2. So taking the log of both sides and solving for t gets us approximately 4.23 days. In the news, you may see they rounded up to 5 days. But this means that it will take 4.23 days to double the number of cases. At this rate, it will take 14 days or 2 weeks for the number of cases to be 10 times more than they currently are. It will take 28 days or 4 weeks for the number of cases to be 100 times more than they currently are. And so the way I did this was I took the equation 1.178 raised to the t power and set it equal to 10 and 100. If we were to take the growth factor of 1.178 and multiply the total number of cases starting on March 31st to get to the next day recursively, we would get this graph. So by the end of the 100 days, or in this case, April 29th, there will be over 25 million people infected by COVID-19. So this graph, as you can see, the scaling is by 5 million. And really what I want you to get out of this is that because this is an exponential function, the number of cases really begin to ramp up. Hopefully, we can do our best to stop this growth.